Good morning, all of you. Today, good morning, all of you, and welcome to this data structure classes. Today, we are going to learn about three different kind of data structures: arrays, linked lists, and binary search trees. Before diving into the details of these data structures, I have a question to ask. You are given a modifiable content. By modifiable content, I mean you have a large data set in which in the real time, you want to insert also. After randomly, you want to delete, insert, and search for a particular element. Like kind of, we have a data set of number of students in the UCSD campus. So what kind? We come up with three kind. On top of the mind, we have these comes to be arrays, data structure array, linked list, and binary search trees. Let's start with arrays. How this will work in this. For these three operations, we'll analyze what is the performance of arrays. For the search operation, let's start. I want to search. I want to search for element 13. What I'll do is as unsorted array, I'll start for the first element. I'll traverse this whole array and till I find the element. I'll traverse the whole array till I find the particular element which you're finding. As we're traversing the whole array, the running time is going to be O of n. In the insert operation, we have, with the help of an end pointer, we can directly insert, we can find the end pointer and we can directly insert the element, let's say value 10 here, and move this end pointer to here. So this will take O of 1 time. This is a constant amount of time, which is really good. For the delete operation, it's a little bit tricky. Let's say we want to delete 15th value. What we'll do is we'll search the array for the value, which is 15th here, which takes O of n time. Now the tricky part is we want to move all the elements which are on the right side to that position. We will delete this element. We'll move 4 here and 3 here. So these are going to be here and here. And we have got an empty space on the right side because this array has a property that all those empty sets are going to be on the right side of the array. So delete operation, searching operation takes O of n time. Moving all those elements to one position backward takes O of n time. Total 2 O of n time. So the delete operation also takes O of n time in a normalized form. Linked list. Linked list. In linked list, the search operation. Let's see how does it works. We want to search element 7. We'll start from the head here. This is the head. We'll traverse this whole linked list till we find the element, and which is here 7. In the worst case, it will take O of n time, as we are traversing the whole of the linked list. For the insert operation is easy because here we are going to create a node here. We'll move this head point. We'll mark the created node head here. The next pointer of this is going to point to the previous head, and we'll add this value, let's say 10 here. So insertion takes O of 1 time. Now deletion operation. To delete a node in this linked list, we have to find the node first, which will take O of n time. So because we are traversing the whole array, we want to delete 9. What we'll do is we'll mark the next pointer of the previous node to the next pointer of the node which we are going to delete here like this, and we'll free this memory here. As you're traversing this whole array, it will take O of n time. Now coming back to binary search trees. Binary search trees. These are binary search trees are normal binary trees with an added property that all the elements on the left child of the node is going to be of value less than or equal to node, and all the elements on the right side of the node are going to be greater than node. Here, as you can see, for root node 10 value, all the elements on the left side are less than this, and all the elements on the right side are greater than this. So, performing a search operation in this, we do a comparison based search here. Let's say we want to search element 18th. What we'll do is we'll compare the value of 18 with the root node value, which is 10. So 18 is greater than 10. That implies that the 18 is going to be in the right subtree of this. We'll move on the right child, we'll see the value of 15. 15 is still less than 18, so 18 should be on the right side of the right child of 15. Here we move on here, we move from 15 to the right side of 15, it's 18, and bingo, we got the answer. So search operation takes, as you can see, the search operation takes a logarithmic steps here, so it takes O log of n time. Insert operation. Insert operation is also works like this only. Like we want to insert value 10. Value 10 is already inserted. We want to insert value 9. What we'll do is we'll see whether 9 is smaller than or greater than this. As 9 is smaller than 10, we'll traverse to the left subchild. 9 is greater than 6, we'll traverse to the right child. 9 is greater than 7. So we'll put it 9 in the right subchild of 7. Insert operation, as you can see, takes logarithmic time of again. Delete operation. Delete operation is tricky. Here we have 3 cases to work on. Case 1 is we want to delete a node which is a leaf in this tree. To delete a leaf node, it's not a big worry because as there are no nodes below that, we can easily find the particular node and delete it. Finding a node takes, search operation takes log of n time, and delete operation we can directly delete in constant amount of time. So case 1 is when a leaf node, we have to delete a leaf node, which takes a simple log of n time. Second case is when a node has a single child, whether it's right or left. In that case, what we do is we find a particular element. Let's say we want to delete 7 here. What we do is the child of the 7, we mark the parent of the 7, let's say this here is 6, we'll mark this right pointer here to 9 and free this memory here. What is happening here is as 9 is greater than 7, it's going to be greater than 6, so the BST property is still maintained here. Case 3, we want to delete a node which has 2 childs. Here what we do is we find the maximum value in the right subtree, the minimum value in the right subtree or the maximum value on the left subtree, and we replace that value with the particular node which we want to delete. Like let's say we want to delete value 6 here. What we'll do is taking maximum value in the right subtree, which is 9 here. What we'll do is we'll replace this value by 9 here and replace 6 here, and then we'll free this memory here. As 9 is minimum value here, which is still greater than 6, so